Hey guys, welcome to my first video. I'm going to talk about a question which was asked in one of the quant firms. And here's the question. Given two numbers, 2 to power a and 2 to power b, and there's also a condition like the decimal representations are anagrams of each other, then we have to prove that a equals b. So let me break it down to you. So for example, like we have a number, say like 2 to power 6, which equals like 64. We have another number 2 to power like say 8, that is 256. So the question says that whenever you take the decimal representations of number, that is decimal representation in this case is like 64 and in this case is like 256. So whenever you take the decimal representation as a string basically and you sort it, okay, you sort both of the decimal representations of 2 to power a and 2 to power b. So when you sort the decimal representations, you get the same string basically. Those things are called as anagrams. So I'll just give you a basic example of anagrams. So what is an anagram here? So anagram means a number like 12712 is one is say it is for the first number and the second number is 72211. So when you sort these two numbers, that would be 11227, and this other number is like 11227. So these two numbers are same. So these two numbers become anagrams of each other. Okay. So when I mention sorting, it's like either both of them are sorted in the ascending order or either both of them are sorted in descending order. So you cannot do it like one in descending, one in ascending. Okay. So that's for the anagram thing. So you get it, right? Like if we have two numbers like 2 to power a and 2 to power b, then if and also the decimal representations are anagrams of each other, then the only way it can happen is like when a equals b. Okay, so you cannot have like a not equal to b and this thing like a not equal to b and those two things are anagrams of each other. So it's yeah. So we have to prove that a equals b. So that's the question here actually. And okay, so here's the solution, right? So assume that we have the condition like 2 to power a and 2 to power b. So 2 to power b, a is x, 2 to power b is y. Okay, so what you can say here, like x and y are anagrams of each other. So since x and y are anagrams of each other, they also must have the same digits, right? So if you see here like 11227, 11227, okay, both of them have the same digits actually. So that means like x and y, if you take the sum of their digits, that will also be the same. Okay, so let's call a function like say d of x equals to sum of digits of x, correct? So according to our condition, if x and y are anagrams of each other, then we have d of x equals d of y. Okay, so that's the thing, right? But we also have another property like the sum of digits, the remainder that we have uh, by dividing the sum of digits by 9, and the remainder that we have by dividing the number by 9 is the same. So we also know that x is congruent to d of x mod 9, right? Similarly, we have y is congruent to d of y mod 9. So if you don't have any exposure to number theory, so you should go and refer to congruences in number theory. Then you can understand this actually. I'm not going through the details of this, but yeah, that's the thing. So this is how it is. So this equation, okay, these equations, okay, we get x is congruent to y mod 9. So this implies that 2 to power a is congruent to 2 to power b mod 9, because as we know, like x is 2 to power a and y is 2 to power b. So we know that thing. So I'll just erase some of these things now. Okay, so I just need some more space here. Okay, and yeah, I can just put it here maybe. Yeah, and yeah, so yeah. Yeah, so we have 2 to the power a is congruent to 2 to the power b mod 9. And then what we can do, like we want to prove that a equals b, right? So what all values, like assume like without loss of generality, like a is less than b, okay? So let's try different values for b. So b can be a, right? B can be a plus 1, b can be a plus 2, b can be a plus n, right? Can be anything, n is an integer. But what if, like, if say we want to find some limit on n, right? So if b is equal to a plus n, then if we consider it like that, so it would be 2 to the power a times 2 to the power n equals 2 to the power b, right? But in that case, if you see, like n cannot be greater than 3, because if you take n greater than equal to 3, that would be 2 to the power a times something which is greater than equal to 16, so which equals 2 to the power b. So in that case, the number of digits of 2 to the power b would be higher than number of digits in 2 to the power a, because you're multiplying 2 to the power a with something which is greater than 10, right? So your n should be less than equal to 3 and greater than equal to 0. So only possible values that b can take is a, a plus 1, a plus 2, then a plus 3. Now, okay, we know like b can take only these possible values. So what we're going to do is put all these values and check whether we have something. So if 2 to the power a is congruent to 2 to the power a plus 1, 2 to the power a plus 2, 2 to the power a plus 3, you see my point, right? So we can take all the possible values of b and check whether any one of that follows the congruence mod 9 everywhere, right? But if you see here, like 2 to the power a is congruent to 2 to the power a plus 1 mod 9, it's not possible, because if we just remove the common terms, because 2 and 9 are co-prime, so that would be 1 is congruent to 2, which is false. This 1 is congruent to 4, that's also false, and 1 is congruent to 8, that's also false. So the only possibility like this condition is satisfied is 2 to the power a is congruent to 2 to the power b when b equals a. So that's the proof, guys.